Hello everybody, welcome to lecture 3. So today is 15th. So we are working on these two operations, time limitation and band limitations. The motivation is pretty clear because we understood that in digital communication what we do, we have our band. This is actually true for analog communication as well. The entire band is not to you. So whether you are a telecom provider or you are military, you are given a particular bandwidth. So that bandwidth, like for wireless communication or even for like wired communication, that particular bandwidth, that particular band which you buy through auction or you are given by the government for the military applications, that band is specified. So this will be in the pass band. So pass band means, this is from analog communication, you know. So pass band is around the frequency where the wireless or wired communication operates. So suppose this is at around say 1.8 gigahertz or something like that. So around that you are given a particular band. That band is of say width 1 megahertz or say 100 megahertz, whatever. This is for the company, and then for that company, for a particular protocol, a particular even smaller band is given, and within that band, say suppose some band of say 80 kilohertz, you have to operate. So in analog communication, you have seen that this particular signal, which is called the pass band signal, in the transmitter and receiver side, before going to the RF region, before the multiplier or the mixer, what you do, you basically have your signal in the baseband. Baseband means around DC. So for that same 80 kilohertz, you put it here, you operate, you do different kind of operation, and then you through the mixer you multiply, or the mixer or modulator, whatever you say. So you multiply with a particular carrier signal, and then you modulate to that particular given passband. So this thing is called baseband. So normally when we talk about digital communication, we are the signal and those kind of design we will do in the baseband, because eventually when we modulate, we will push it over there, but over there that process is basically multiplication, nothing else. Multiplication with a sinusoid, with a carrier signal. So our design, everything is here. So so when I am talking about bands, I'll be basically working on that baseband itself. So in that baseband, suppose you have, I'm just writing something for the sake of simplicity. Suppose you have some from 1 kilohertz to say 5 kilohertz, you have that total band which is provided to you. Now you have to make 5 channels out of it. So each with 1 kilohertz bandwidth. So you split it, and this is 2, 3, 4. Oh, sorry. So suppose this is 5 kilohertz. Yeah. So you are splitting it into 4 different bands, each with bandwidth 1 kilohertz. And it's like you have 4 channels. So these channels are parallel channels, because you can send through these 4 different bands simultaneously in the same time. So what you are doing, you can send from 4 different transmitters, or from a single transmitter. What you can do, you can send 4 pulses by frequency division multiplexing. So this is called the frequency division multiplexing. So you are splitting the signal, and you are basically designing the signal for each band, and you are sending them through one of the band. So these are essentially these so-called baseband channels, which we are saying, they are essentially filters, and those filters are operating with that 1 kilohertz bandwidth around, say this is 1.5, this is 2.5, this is 3.5, and this is around 4.5. So that is the mid frequency. So each of these is like a band pass filter. So that band pass filter looks like this. I'm drawing a rectangular kind of filter, which is the idealized behavior. Of course, in reality, you never get a bandpass filter like this. So, in fact, that bandpass filter you can shift again to around DC, so such that you can have truly a low pass filter, and that low pass filter then again move around to this bandpass filter. So you have seen these things in analog communication. However, the motivation is as follows, that these bandpass filters, these 4, so they are working like this. I'm using a different pen. So this is one, the next one is suppose here, next one is here, next one is with a different pen, suppose here, like that. So what I expect, that if the filters are really sharp, the roll-off is really sharp, then there is no overlap and you can fit your signal which you are sending. These signals are sent parallelly, that will fit here and there will be no overlap between these two bands. That is the idealized scenario. Okay. If there is no overlap, that is well and good, but if there is some overlap, suppose there is some spillover of the signal, so you are trying to send, since these bands are not really non-overlapping, these like bands, these filters are having a roll-off, some physical roll-off, and if you do not have enough separate, then there will be some overlap of these filters. Then the signal what you are sending through this filter and through this filter, there can be some overlap in the spectrum, in the spectral domain as well. So this kind of interference of one signal with another is called the inter-channel interference, since they are different channels. And this inter-channel interference, this is not restricted to digital communication, it is there in analog communication as well. So one solution is basically to keep the so-called channels separate. There should be some stop band. So this is one band and then there is the next usable band, such that whatever roll-off you are having here, that roll-off should not overlap with this. However, let us start working on that worst case scenario because of the today's requirement of digital communication, the huge amount of internet data, telephone data, etc., etc. So the amount of bandwidth requirement you have and the restriction of total bandwidth in the wireless medium, that is restricted by the physics. So you cannot really increase the bandwidth of free space. That is not in your hand. That is governed by the laws of physics, electromagnetic radiation. So our requirement, like user requirement is increasing, the requirement on band is increasing. So we do not have that luxury that we will keep two bands in a far away region. So they are pretty near and there can be some overlap. So the filters are not really like split, not really separated. What we have to do, the signal we are designing, that we have to keep, we have to ensure that they are fixed within that band, that they are restricted within the band, there is no spillover. That is our requirement. Now in digital communication, the special thing which is coming in is not only frequency division multiplexing but also like time limitation. So within that, because in digital communication we know that from a digital data or the bits, the binary data, so those bits are coming, and for every bit you are giving a time window over which you are generating some baseband waveform. That waveform should fit within that particular bit. So it that particular waveform can be, so if you take some pulse code modulation kind of signal in the baseband, so it can be a square wave. But so suppose your bits are coming, so you are saying that for every one I am giving one binary wave like this. This is my 0, and for 1 I am giving something like this. So this time duration through which you are sending the signal, this time duration is say 1 millisecond. So for 1 millisecond I am sending this, in the next 1 millisecond I will send another pulse, and by those pulse I am sending the digital waveform. We will talk about this in detail later on. Right now I am just telling to motivate between this time and band limitation process in the signal. The exact architecture of the digital time and frequency division multiplexing along with the different modulation schemes, those we will talk later on. So when you are restricting the time as well, so you are saying these zeros and ones we will normally say as symbol. So trivially there are only 2 symbols, but in reality what we can do, instead of just 2, we can have any like 2 to the power n constellation, and for every n bit we can consider that to be a symbol, and we can designate one pulse for that. That pulse may not be like squarish wave, that can be something else, some Gaussian, some raised cosine. We'll talk about that. So, but within that specified time window, which we will say to be T0, that is our specified time window, we will send one symbol. So, typically when you have a digital sequence, so whether it is binary or you have a 2 to the power n symbol constellation, so you have the sequences like say A0, A3, A4, A7, A1, suppose 3-bit constellation, so A0 to A7. So say A0 is equal to 0, 0, 0 and A7 is equal to 1, 1, 1. This is the constellation which you are having. So suppose this kind of signal is coming, and so for every symbol you are given a particular time window. So suppose this is your 0 second, this is a 1 second, this is a 2 second, this is a 3 second, this is a 4 second, and you have to, for every symbol you have to fit one waveform here. So the waveforms will be, and they should be uniquely detectable. So suppose A0 I am putting it a sinusoid like this. So A3 it is say having a different phase like this. A4 I am having another phase like this, something like that. It will be like this. So it should complete the full wave. Say A1 it is say something like that. So this kind of waveform you are fitting to send these signals, one of the symbols. Okay. Now you can see that if we are restricting in time, so how does this time restriction happens using a circuit? It can be done using a simple switch. So suppose you have red MOSFET, right? So suppose the waveform is coming, what you can do, you can put a switch over here, and this switch will be on for say 1 millisecond. So that 1 millisecond this signal will come. So if there are say 7 different symbols which are coming in, what you can do, you can keep 7 inputs or 8 inputs. Suppose these 8 signals are coming. So whichever signal is ready, your switch will be connected to that particular thing, such that all signals from all these symbols will appear here one after the other. So this is a kind of like time division multiplexing framework where so you are getting the symbols from these these are the waveforms actually, not A0. I should write this to be X0T, say X1T, X2T, and X0T is used for the symbol A0T, A0, X1T is for A1, X2T is for A2, and so on and so forth, right? So these symbols you are generating by some oscillator, and which symbol is passed in that particular instance of time, that will be selected by some switch, and this switch is controlled by the symbols. So A0 to A7. So when the symbols will come, you will choose one of them. Don't worry, we'll talk about these in detail. So the idea is you are generating waveform in baseband waveform which is time separated. So you are getting a particular waveform, but they are separated in time. So this will be one symbol. The next one is a different symbol. And I expect the symbol to be restricted within this time interval. There should not be any spillover to the next. If that happens, if one symbol's waveform goes to the next one, that particular thing is called inter-symbol interference. This inter-symbol interference is pretty unique for digital communication. It is not there in analog, because analog it is assumed to be like one timeline only. Timeline is not split. So our objective is to get digital communication baseband signaling where this inter-channel interference and inter-symbol interference does not happen, like they don't happen, or even if they happen, their like influence on detecting the exact symbol correctly is, the error is minimized. We can remove the like bad artifact of this interference. So let us now try to study that what are these two operations, band limitation and time limitation, does to a particular L2 function. Yeah, our functions are our signals which you are using from our dictionary. They are like L2 functions. They are having finite energy, right? So how these two particular operation works. So the circuit we can understand. So time limitation is basically a switch. So you're selecting that particular line, and then when the time is over, you are just switching it off. And band limitation is basically filter. It is like band pass filter or low pass filter. Okay, those are the operations. So mathematically, let us try to develop those two operations, and then we will talk again about those two spaces, the curly B and curly D. Okay, so our processes say we will again come back to the spaces of band limited signal space, say B, and time limited signal space, say D. And we are taking the second notation which we used for the uncertainty principle derivation, where that two restriction limits are not related. So we define B to be, we have already defined it, but nevertheless these are such functions in L2 infinity, say, such that the Fourier transform, the support of the Fourier transform of Ft is equal to, say, minus omega to plus omega, and D is given by some function which is again L2, such that the support of the signal itself is equal to, so I can write this B sigma to give the proper notation. This is equal to minus T by 2 to T by 2. So these are the two signals, and we know clearly that B sigma intersection dt is equal to basically the zero trivial signal. Now one student asked about this particular derivation, that what happens like if you take an entire function or an analytic function, which is the band limited signal function. These are analytic functions. Then if the any analytic function is zero in any interval, then why it is zero everywhere? This is a famous result from complex analysis. So it comes from the Taylor series expansion. So if you are if a function is zero in a particular interval, so if you take the derivatives, all the derivatives are zero, and for every derivative is basically forcing the function outside this interval to be zero, and this is infinitely true. So basically that enforcement that encroaches the entire real line, so everywhere it will be zero. Just go to your complex analysis book. I'm not giving you the exact derivation, that is beyond the scope of this particular course, but I'm expecting that you know that amount of complex analysis. Okay, so these two spaces, they are overlapping only on this trivial signal 0, nowhere else. So graphically we can show that, suppose this is the L2 space, L2 infinity, and infinity means basically the real line, for the entire real line. Then these two spaces are two trivially overlapping space. So they are basically overlapping, say, at this 0 signal, and this is, say, the time dt space, and this is, say, B sigma space. Okay. Now when you have any L2 signal, say F, so you are basically projecting this signal over there or projecting this signal over there. That means basically you are doing band limitation, time limitation or band limitation. So I am writing this in this way. So this projection is basically, this is the time limitation projection, and this operator is given by, say, D. dt, or I am writing just D, but it is understood that this is basically dt, and this particular projection is called the operation B. So this is the filtering operation, low pass filtering operation, such that it forces the signal to have its Fourier transform intact in this range, externally 0. This forces the signal to have its value in this time range, externally 0. So let me write down those two operations. So D on any F T is basically ft when t belongs to this minus t by 2 to t by 2 range and 0 otherwise. So circuit operation, what is this? This is basically your ft is coming, your ft signal is coming from here. You are having a switch here and this is your basically DFT. So this switch is controlled by a signal which is a pulse, and that pulse turns on at minus t by 2 and turns off at plus t by 2. So when this is on, then this switch is connected, and when this is off, then this switch is off. Basically this switch is nothing but a MOSFET switch, you can visualize. So MOSFET switch whose the signal you are sending is basically this signal which is between minus t by 2 to t by 2. So when this signal is 1, then the MOSFET will allow the FT signal to pass. When this control signal is, this is the control signal, when the control signal is 0, it will not allow the pass and the output will be 0. Okay, whatever signal be FT. So if the FT is say like this, and your t minus 2 by 2 t minus 2 is say this range, so output will be basically and outside that it will be 0. This is the output of such a switch. That is time limitation, or this is FT, this is DFT. This is how I understand time limitation. What is band limitation? Band limitation is filtering. So for any FT which is regular L2 defined between minus infinity and infinity, I define the Fourier transform, say f omega. Earlier I was writing f hat omega or something. Right now I am writing capital F omega, you understand, right? So f omega is integral minus infinity to infinity ft e to the power minus I omega t dt. Now if I truncate capital F omega between minus capital omega and plus capital omega, and then take the inverse Fourier transform, that will give us the BFT, the band limitation. So band limitation is given by 1 by 2 pi basically d omega f omega into that. So I can write this as d omega, this is basically dt, okay, d omega f omega into e to the power plus I omega t d omega minus infinity to infinity. This is how BFT is defined. Now, sorry, this FT I am restricting to minus omega and omega. Yeah, just a minute. Yeah, I think this particular expression I'm just cutting. I'm modifying that definition again. So what I want to do, I want to basically do low pass filtering. So what is your BFT? BFT is basically like you are doing like you are enforcing this f omega to be restricted within this range. So it will be 1 by 2 pi. That limit will not be minus infinity to infinity, it will be from this to this, because that is where you are defining it. And your signal, that signal is basically the original f omega. So that f omega e to the power plus I omega t d omega, where f omega is basically given by this particular integral. So you take the original signal, you take the spectrum, and then that spectrum you are doing inversion under this changed interval, which is minus capital omega to plus capital omega. So these two process is basically the low pass filter by which you are getting this. Okay. So what is this operation? This operation is basically a smoothing operation. If this is an ideal low pass filter, what it is making, whatever f it is, L2, you are making a infinitely differentiable smooth like response, almost smooth output out of it. This is a low pass filter. So ft, you are pushing passing it through a ideal low pass filter of bandwidth say capital omega. So that you are giving b omega ft. Yeah, I can write this b omega. Like everywhere else we will use only dft. It is understood that d is dt. Similarly, we will write only bft. B is basically b omega. That is understood if not specified otherwise. Now we can think of different kind of operations. For example, you take initially you take the signal L2 signal ft, then initially you push it through a filter. So let us draw the circuit again. ft, you push it through a MOSFET switch, which is operated, the control signal is operated between minus t by 2 and to t by 2. So that is basically doing the time operation, time limitation. So this operation is basically dft, and then you are pushing it, you are like passing it through a low pass filter. So this low pass filter is between minus omega and plus omega, and you are getting basically bdft. Clearly, from uncertainty principle, we know that you cannot limit both. So when you are enforcing, when you are doing this operation, what you are doing basically, you are projecting from F. So these are the two spaces, say. This is the D space and this is the B space. This is the total L2 space. When you are passing it through this switch, you are basically enforcing here and you are getting df, and then you are projecting from here to here and you are getting bdf. Now this signal is time limited signal, but it is not band limited. When you are doing low pass filtering, this is band limited signal, but this is no longer time limited because this cannot belong to this thing B. Okay, so my objective is what is my target? I want to get something which is approximately band limited and approximately time limited. I cannot get both simultaneously, but my target is such that the minimum energy is outside the time band and outside the frequency band. Maximum energy is within the band, both time and frequency band. But what do you mean by this maximum or minimum? These things are imprecise. So we have to make it precise. But before that, let us understand this particular operation, because this particular operation will be used everywhere. We would rather, of course, after BD, you understand that this will not be time limited anymore. There will be inter-symbol interference. But at least there will not be inter-channel interference. We are more concerned with inter-channel interference because the other channel is not mine. That is of some other company. If I send some signal which is going in their channel, they can sue us. At least inter-symbol interference, nobody is going to sue me because both the timelines, both the time windows are my time window. Of course, they are of different symbols, but at least nobody is going to sue us. So the final operation will be BD, and that is one like physical, that is one practical restriction, that I don't want inter-channel spill. Another thing is that we know that this band pass operation, when you are like enforcing it to this space B, this space B is a nice space. It is a smooth space. This is a space of entire functions, right? Entire or analytic functions. So they are infinitely differentiable, mathematically at least. So they are very nice in everything, like you can differentiate, you can doubly differentiate, you can triply differentiate, etc. etc. So it will be better if we get a signal like this. So we want to basically understand this operation first, this BD operation, that what it does to a function. We basically want to do eigenanalysis of this particular operation BD. So before actually going to eigenanalysis, let us first understand what do eigenanalysis does. Eigenanalysis do. So eigenanalysis. So we know for matrix, right? So suppose you have a matrix. What does matrix do? Matrix are operators. So matrix basically takes a vector in a vector space and it maps to another vector in another vector space. Let us talk about some square matrix. So if you have a square matrix, then square matrix operates on a vector space and it maps back to the same vector space. So I don't have to go anywhere else. So suppose you have a vector space, say n-dimensional vector space, so the A is a n cross n matrix. Okay, so you have some vector V, suppose. You want to know where will be the resultant vector after the operation of the vector A, of the matrix A. So clearly we don't have a clue, and we know vectors are basically in that n-dimensional vector space. It is a like quantity which is having some amplitude and some direction. So I want to know that what amplitude will the resultant vector be and what direction will the resultant vector be. So it will be easier to understand this matrix, this like operator, if we know that is there any vector in the vector space such that if I apply my operator on that vector, the direction at least remains same. So it can be amplified, it can be attenuated, the amplitude can change, but direction should remain same. Then that direction is called the eigenvector or eigendirection. So that vector is called the eigenvector, whose direction does not change. The amplitude can change. So I write the eigenequation as this. So A into V is equal to lambda into V, where lambda is a scalar. This is called the eigenequation of a vector, of a matrix A. This is a scalar, this is called the eigenvalue. And this vector, whose direction does not change, because before earlier it was say V in a particular vector space, and now it becomes say this is the drawing is bad. Suppose this is a vector V, and after like multiplication, after like operated by the matrix, which is matrix multiplication from the left side, you are getting lambda V, where lambda is a scalar. So this is the scaled up version. If lambda is real, say real positive, less than 1, so it will be a smaller vector lambda V. If it is greater than 1, it will be a larger vector. If it is negative, it goes in the opposite direction. But that is in the same line, in the same direction, right? With a negative multiplier. So this helps us, if we can know all the eigenvalues and correspondingly all the eigenvectors, then what we can do, suppose there are n eigenvalues and n eigenvector, which is the case, right? For a square matrix, full rank square matrix A. Then if you take any vector and if you can like decompose any vector in terms of those eigenvectors, suppose you take any vector u and you can write, suppose there are those n eigenvectors v1 to vn. So v1 to vn are the n eigenvectors, corresponding eigenvalues are lambda 1 to lambda n. Then if you have a new vector and if you can write that as a linear combination of say a n vn, n is equal to 1 to ak vk, say ak vk, k is equal to 1 to n. Then we know that the matrix is linear operator, so your au will be a into summation ak vk, k is equal to 1 to n, which is same as summation k is equal to 1 to n ak into a vk, and a vk is equal to lambda k vk. So it will be equal to summation ak lambda k vk. So you have some analytic expression of the output, and if you can do this for all vectors in the vector space, that if you can express that vector in terms of the eigenvectors, then you know how the matrix will behave when it is left multiplied to the corresponding vector. You know the output pretty easily using the eigenvector and eigenvalue. So these are the coordinates for that vector in terms of the eigenvectors and multiplied by the eigenvalues of the matrix. So the impact of the matrix is essentially impact of the eigenvalues on those particular eigenvectors. This is how you do analysis in a finite dimensional vector space, eigenanalysis of a matrix. Now I want to extend it to another known space which you know, that is the functional space. Of course you have seen already the convolution theorem and linear time invariant system, but I want to elucidate that thing again. I want to show you again that that is indeed eigenanalysis. So suppose you have a linear process, that is the LTI filter. So LTI system. For the time being, you can assume that you may not assume any causality. It can be non-causal as well, or both causal and non-causal. If there is no restriction, then or you can assume causality as well, no problem. So suppose you are having xt and your system is ht, and you have some output yt. This is a filter, right? In network theory you have, or signal systems you have seen this. So what is yt? Yt is equal to basically convolution of xt with ht, which I can write as integral x tau h t minus tau d tau, which can be written as h tau xt minus tau d tau, the same thing. And if it is a causal system, it is 0 to infinity. So your ht is defined only for the positive values of t. Okay. So this operation is clearly a linear operation, and if your h does not change with time, then it is called the linear time invariant operation. So this linear operation or linear operator, I want to see that how we can know about this y, because convolution is a tough process. Like you may not get this integral all the time, and knowing ht is also difficult. So how do I know what will be yt if a particular xt is given? So you can do the similar kind of eigenanalysis. So to know first what this linear operator is doing, the convolution operator with h is doing, you have to do the eigenanalysis. So eigenanalysis is basically a decomposition technique by which you can decompose the operator in terms of the eigenvectors, here eigenfunctions, and the eigenvalues. And you know from linear algebra the eigenvalues are called spectrum, right? So in this case, is there any eigenvalue or any eigenfunction for the convolution operator? Do you know anything? So yes, we know one, that is called the complex exponential functions. So let us see that how this particular function, if e to the power I omega t is passed through ht, what output you will get. So simply do convolution. So output is say yt. So yt is equal to convolution of e to the power I omega t with ht, and that is equal to say ht. I can take the integral to be minus infinity to infinity also, because ht is by itself is defined for positive like time, so it does not harm anything. H tau e to the power I omega t minus tau d tau. That's the convolution integral, which will be equal to e to the power I omega t goes out, and the rest is h tau e to the power minus I omega tau d tau. What is this? This is the Fourier transform of h tau. So you get h hat omega e to the power I omega t. You see? So input is e to the power I omega t when it passed through the LTI system ht with impulse response. The output is h hat omega I omega t. So e to the power I omega t is indeed eigenfunction for all omega. And what is this? This is the eigenvalue or spectrum. So Fourier transform is called spectrum. This is the like construction. This has been done in Fourier analysis also, nevertheless. Now with this, what you can do, you can analyze any system with so ht for any arbitrary x. Suppose this is the structure. So when you are giving x, so what will be the yt? So if you can split, you can decompose xt using say Fourier transform or Fourier series. So it can be like based on the restriction of this. So if this is periodic or time limited, then you can write it in terms of the Fourier series. Say an e to the power I n omega t, omega 0 t say, and then yt will be basically linear combination of an h n omega 0 e to the power I n omega 0 t for all n. This is for the Fourier series case. And if you have a Fourier transform scenario, you have like transient signal xt or L2 signal xt, then xt can be written as 1 by 2 pi integral minus infinity to infinity x hat omega e to the power I omega t d omega. In that case, your yt will be equal to 1 by 2 pi x hat omega h hat omega e to the power I omega t d omega. So we know a clear-cut analytical way of observing the output, like understanding the output of a system, which is linear system, linear time invariant system. And the eigen analysis helps. So it's a good thing that you have the eigen function, which are essentially the complete basis function for this Fourier series application, or the basically the kernel function for a Fourier transform scenario, and that helps us to understand the linear system of ourselves. So this eigen analysis basically helps us to categorically analyze the process, here the convolution process, or earlier the matrix multiplication process. So my question is, what about this process? This is also a linear operation BD. I'll just show you that what kind of function is BD, and then I will try to perform some eigen analysis on this. Is there any eigen function? So do we get something? So this was a question which was many people have tried for more than a century, like is there any eigen analysis? Then in 1960s, in the Bell Lab, the same Bell Lab which developed information theory and Linux, three people, David Slepian, Landau and Pollock, they basically devised this idea, and they did the eigen analysis, and they found out it was a serendipity moment. They told that this is a lucky accident. They got a set of eigen functions, actually infinite set of eigen functions, just like the complex exponentials, which are infinite set of eigen functions of the convolution operator. This particular set of eigen functions is also an infinite set of eigen functions. Not only that, they are orthogonal basis functions. So it was a lucky accident because they wanted something, they got it. Not only that, the function is nothing new. It was known more than 200 years ago. So while solving some partial differential equation, people got these particular functions, and these are already known to people as the Prolate spheroidal wave functions. So this in 1962, these three people, Landau, Pollock and Slepian, they rediscovered the same functions for a completely different problem. So this is fun in mathematics and applied mathematics, which is we call engineering, that many problems when you try to solve it may seem difficult and unrelated to some erstwhile solved problem whose solution you already know, but you did not know that the same solution can occur in this particular problem. So that's why knowing literature is important, because if you know existing methodology of some other a little unrelated fields, that will not harm, because you never know that your problem may have solution elsewhere already done. All you have to do is connect the dots. So let us first talk about this particular operator, which is BD, and then we will talk about the eigen analysis. So this particular operator BD, what it does when you apply them in series, first you apply D, then apply B. So what does D do? So you have some function f. If you apply D, it basically truncates in time. So we already wrote the expression. That expression is here. It truncates in time. So this BD, so DFT is essentially FT for t less than equal to t by 2 and 0 otherwise, and on it you are applying B on that. So that will be equal to, so it will be the function we have already written, that is this. So it will be 1 by 2 pi minus infinity to infinity f omega. F omega is what? F omega is Fourier transform of small f. That small f is here df e to the power plus I omega t d omega. So this is BD. So this is the Fourier transform of DFT. So what is Fourier transform? Fourier transform is minus infinity to infinity dft e to the power, say dfs, I am writing something else because this is t is outside, dfs e to the power minus I omega s ds e to the power plus I omega t d omega, right? Now dft is what? ft in this range, 0 otherwise. So clearly this d, if you write it, it's like a box function. So this limit minus infinity to infinity, it will be truncated to a finite limit. So it will be 1 by 2 pi minus omega to omega, and this integral will be minus t by 2 to t by 2. This will be fs e to the power minus I omega s ds e to the power plus I omega t d omega. Fine. Now we can apply the Fubini's theorem. So if I apply the Fubini's theorem here, Fubini's theorem is what? Basically interchanging the two integrals. That is done only when you know that everything is convergent and we know that fs is L2. So if you multiply with some complex exponential, it does not change anything because this complex exponential is a phasor on the unit circle. So it does not change any amplitude. Like the absolute value remains in that remains same. So whatever absolute value is of fs is, the same absolute value of fs e to the power minus I omega s is, right? So you can apply Fubini's theorem here. So if you apply Fubini's theorem, then this bdft, it will be 1 by 2 pi. The outside integral will become minus t by 2 to t by 2. You take fs out, and the inside integral, it will be the frequency integral minus omega to omega, and you have e to the power minus I omega s e to the power plus I omega t d omega. This is your inside integral on the frequency, and outside is ds, which is time. Now you perform the integral over the inside integral, minus t by 2 to t by 2 fs, and this is minus omega to omega e to the power plus I omega t minus s d omega ds. So this is known integral, right? So 1 by 2 pi minus t by 2 to t by 2 fs. This is e to the power I t minus s omega minus e to the power minus I t minus s omega divided by I t minus s ds. So what is this? 2i sine fs 2i sine omega into t minus s. I can take this 1 by 2 pi inside, 2i into pi t minus s ds. So I get the sine c cardinal fs sine omega t minus s by pi t minus s ds. This is the operation. So what you are doing, you are taking the function and you are convolving with this function. So this is basically a convolution integral, finite convolution integral, mind it. So the convolution is happening from minus t by 2 to t by 2, and you are convolving with sine omega t divided by pi t, sine c cardinal. Now this is the operator. Now what is the eigenequation? The eigenequation is bd ft is equal to some lambda ft. Now this is the eigenequation. The question is there any eigenfunction ft satisfying this particular equation star in L2. Now, whenever you come across these kind of questions where you are asked that are there any eigenfunction like this, these questions are normally non-trivial. Non-trivial in the sense that you do not know the answer, and there may not be an there is no methodical way of finding such solutions just by looking at this. You can clearly see that if you have a expression like this, and if I write a eigenfunction in this way, that integral fs sine omega t minus s divided by pi t minus s between minus t by 2 to t by 2 ds is equal to lambda fs. And if I ask you that for what value of fs this equation is satisfied, this is a particular kind of integral equation, right? So clearly you can see that this is a convolution operator, but limited time convolution operator, and this is a low pass filter, ideal low pass filter kernel. That is what we have drawn. Ideal filter, ideal low pass filter kernel, but you are performing the low pass filtering only for a finite time duration. That is exactly what you have written. But I am asking you the question: if you pass some signal through this particular setup, which is this expression, will you get the same function with a scalar multiplying factor? This is a scalar factor. It can be a complex number, but it does not depend on s. It does not depend on any time. Sorry, t. This is the t. You are running over s. Yeah. So this is the eigenvalue. So is there any solution for this integral equation? The answer is not always very simple, and these are called the groundbreaking research if you find a solution to this kind of integral equations, this kind of eigenequations. So these three people, Slepian, Landau and Pollock, they basically developed a series of papers, some 4 or 5 papers, and which they published in the Bell Systems Technical Journal, and which says that yes, there exists not one such function, rather infinite such function. But there is a good news and there is a bad news. The bad news first: there is no such function in L2. So the bad news is there is no such function, eigenfunction, in general L2, in all of L2. The good news is there are countable infinite such functions in B, not only B, in D as well. So the same functions are true for B and T. So out of the entire space, the most important space which we are talking about, the time limited and band limited signal space, say T and omega, over there are countable infinite number of such basis functions, such wave eigenfunctions. Not only that, it is even better that those functions which we will name as the psi nt, the so-called eigenfunctions, those functions are orthonormal in B. That is better. And the best is those functions are orthogonal in D. This is remarkable. I am not going through the entire derivation, that will be really out of the scope of this subject, but If some of you are interested, I can share the papers with you. This is worth reading, and I read those papers in the last week or so. So I'm giving you only the most exciting part, and which you can understand without developing any new mathematical skill. That particular thing only I'm describing, and I'm trying to motivate our problem, which is the digital communication problem. So let us write these things in precise form next. So these particular functions, which are I'm naming as lambda 0, lambda 1, psi 0, psi 1, psi 2, and these are the real valued function. All these eigenfunctions are real valued function. Up to infinity, these are some real valued function, eigenfunction, with eigenvalues lambda 0 is greater than lambda 1. Basically, I am choosing these eigenfunctions in such a way such that the spectrum is monotonically decreasing, the eigenvalues are decreasing, lambda n, and so on and so forth. However, everything is greater than 0 and less than 1. So between 0 and 1 you have infinite such eigenvalues, such that the eigenequation is satisfied, that is integral minus t by 2 to t by 2 say k s sin t minus s by pi t minus s ts is equal to lambda k psi k t. This is the first expression. Second result is this is the eigenfunction thing. Second thing is these functions psi k's, if you take the inner product, that psi I t and psi j t over the entire real line, so it is minus infinity to infinity. These are band limited signals. So psi I t, psi j t dt, this integral gives you the Kronecker delta, which is basically 1 when I is equal to j and 0 otherwise. So basically all the eigenfunctions are orthonormal over the in the space B. So this basically states that their psi I t's are orthonormal in B. Second is third is if you do time limitation, if you perform the operation D on them, still they remains orthogonal. So which is basically saying minus t by 2 to t by 2 then it will be equal to lambda I delta ij, which is equal to lambda I if I is equal to j and 0 otherwise. So it is not orthonormal, that is not possible, because when you are time limiting you are basically dissipating some energy, you are losing some energy, but that amount which remains is lambda I. So if lambda i's are big, you retain more energy in that time interval. So this is basically saying that those psi I t's are orthogonal in T. These particular functions, the functions waveform, I will show you. I can share the paper with you. You can see the functions waveform for different values of omega and t. Of course, these functions and eigenfunctions and eigenvalues, everything depends on these two parameters, sigma and capital omega and capital T. Actually, it depends on the product of these two things. So 2 omega t, on which it is dependent on. Basically, this is dependent on the dimension, which we will talk next. So on that, the functions and the eigenvalues are dependent, and there are lots of results relating these eigenfunctions and eigenvalues, but I want to mention only a few For example, like which are applied in this kind of digital communication kind of applications. So one thing is approximation. So suppose when you are receiving some signal, so you are receiving some signal, some band limited signal in a particular time window. So you know you are sending a band limited signal, but when you are receiving it, let me show you the diagram again. You are sending a band limited signal. Finally, BDFT is band limited. It is not time limited. But when you are receiving it, your reception window is very much time limited. So you are again applying the window window D, the time limited window on that incoming signal, and you are getting a particular waveform which is time limited. The question which you will ask next, that can I get back a band limited approximation of that time limited signal? So what can be done? Or you can ask questions like this is the same kind of question that you have a time limited, time truncated a band limited signal which you have information only in a given time window. Can you extrapolate the signal to get back the original band limited signal? So that extrapolation question is pretty important. Suppose extrapolation, approximation is a similar kind of question. So extrapolation of band limited signal from its information in a particular time window, in say a time window minus t by 2 to t by 2. So normally speaking, so this function ft, suppose it is in B. So normally speaking, this is entire function. If it is entire function, we know from complex analysis that if it is given in any interval, I can extrapolate into the entire complex plane, not only the real line but the entire complex plane by the Lorentz series, Taylor series kind of stuff. But the problem with Taylor series is that the convergence of Taylor series is very bad. So for a given interval, the Taylor series converges pretty well, but as you move forward, and if you truncate the Taylor series, the divergence grows. So it will not be good approximator for the particular signal. However, with our expansion, so if you can expand ft using a Fourier series, and that Fourier series is basically the basis functions are these Prolate spheroidal. These basis functions are called the Prolate spheroidal wave function. Okay, these basis functions are called the Prolate spheroidal wave function. It is from that history of differential equation PDE, where basically people performed the solution of the differential equation by converting the coordinate system from Cartesian to Prolate spheroidal coordinate system, and then you can do separation of variable in that particular coordinate system, and you got the solution. And that those solutions are basically these Prolate spheroidal wave functions, which basically solves this, and which this Slepian called as the serendipity, the lucky accident. So you can do apply Fourier. You can do Fourier series in this way. So ft and those psi nt, the Prolate spheroidal wave function, multiplied by the Prolate spheroidal wave function. So which is n is equal to 0 to infinity. And you can compute this. I can write as an or something like that. So this is also a Fourier series. Now this an can be computed as this inner product. Now see another trick. So this inner product is ft omega nt dt for minus infinity to infinity. But we also know that this an, it is like this omega n, psi n, the Prolate spheroidal wave function, they are orthogonal in the finite time window as well, in the space D as well. So if so, then what we can do, we can take the integral. For example, we take the integral, this integral minus t by 2 to t by 2 ft omega nt psi nt dt. Then this will give us minus t by 2 to t by 2. Ft is this summation an say ak psi kt, k is equal to 0 to infinity psi nt dt. Now again apply a Fubini kind of swapping. So k is equal to 0 to infinity ak integral minus t by 2 to t by 2 psi kt psi nt dt. Now what is psi kt psi nt dt for that smaller interval minus t by 2 to t by 2? It will be lambda delta. So it will be k is equal to 0 to infinity ak lambda n delta kn. So for all the values, for all the terms, only k is equal to n remains. So it will be an lambda n. So from here you can compute an in a simpler way. So an can be computed as 1 by lambda n integral minus t by 2 to t by 2 ft psi nt dt. You can see that things are becoming easier because computing an integral in the infinite duration. So for that you need like a filter, like correlator which can correlate between minus infinity and infinity. But here no. If you know the eigenvalues, you can only correlate in this interval minus t by 2 to t by 2, and then you can put this factor 1 by lambda n and you get the value. So that helps. So things are becoming finite from infinite time window, which is the norm in analog communication. All the integrals are between minus infinity to infinity. Now to compute a coefficient which is very much a Fourier series coefficient, I can perform it using only a finite integral. That integral is between minus t by 2 to t by 2. So this is a great save, and this helps us immensely. So once you get this, what we can do, the approximation, we can truncate at some suitable capital N. So the corresponding approximation will be that, and initially the ft was known only between minus t by 2 to t by 2, but when I am writing ft as this is for all t. So it should be for all t, and n you are computing in this small interval. That is the knowledge which is available, right? So your extrapolation problem is getting solved because you do not have it outside this interval. Everything is within this. So the approximation will be ft will be some truncation. So n is equal to, that is like Fourier series, an psi nt. And what will be the energy which is left out? The energy left out will be basically like from Parseval kind of application. You know that for the entire signal, if you look at the entire signal, the band limited signal over the entire real line, so that error energy will be basically summation n square. N's are these are real because everything ft is real and the wave functions are real, so these are real. So I'm simply writing n square. N is equal to capital N plus 1 to infinity. This is if you are talking about the signal in the entire interval, but if you are talking about the signal in this minus t by 2 to t by 2 integral, then there will be a factor lambda 1 as well. So error energy in the time interval in set d, that energy will be equal to n square lambda n is equal to n plus 1 to infinity. And by choosing the lambda n properly, you can fix the capital N, so by which you can do the approximation. So these are the techniques by which you can do different kind of applications. This is having this Prolate spheroidal wave function is having multiple applications. For example, I'm not going to prove it, but I'm just stating it. A statement of uncertainty principle as well. So uncertainty principle tells us that you cannot have simultaneous concentration of time signal and with its Fourier transform, the corresponding spectrum. So it says that d into d, that is greater than equal to half at least. So you cannot have a signal of 1 millisecond duration and 1 hertz spectral band. No, not possible. So to have 1 millisecond duration, you need at least 500 hertz of spectral band. So those things are fixed by the uncertainty principle. But the question people can ask that do you have anything better than that? Like this uncertainty principle, when you say, like here we are talking about the bands and the time window. So if you have 1 millisecond of time window, your spectral band has to be at least 500 hertz. 1 kilohertz is fine. So for 1 kilohertz you can have 1 millisecond time window, but for 1 kilohertz you cannot have 1 microsecond time window. That is not possible. So that is what the uncertainty principle says. But Prolate spheroidal wave function gives us a tighter bound on the amount of energy which is restricted in that time window and spectral window. Okay. So yeah, this D and D is somehow related to this like bandwidth. The capital D is somehow related to the bandwidth of that particular channel, and small d is somehow related to the time width of that thing. So ideally speaking, like if it is absolutely squarish both, then it is the same value, but in reality it is not, because it is not absolutely like rectangular pulse here and here. There will be some spill off. So you have to compute the variance in which by which we have computed in the earlier class the uncertainty principle. So this Prolate spheroidal method is basically tells us that this is not half. Actually you can even get a tighter bound. It can be even like increased by the amount of concentration you have of the signals within the particular bands. Not only that, there was a question that in between these two spaces D and B, we know that they overlap only at the trivial 0 point. But if I want to ask you that what is the minimal angle between any vectors here and here, so the question I can ask is basically the infimum of the inner product of any signal in F which belongs to B and any signal is G in which belongs to D. So infimum of F and G when F belongs to B and G belongs to D of the inner product. Can we find out that? Because that will give us the idea of the angle. So basically the cosine inverse of the inner product divided by the norms, that is the angle. So it has been found out that the angle theta, the minimum or inf angle, which is basically the inf of Fg divided by F and G cos inverse. So cos, I should write cos inverse over there. So theta mean is equal to not inf of this, sorry, because cos 0 is basically unity. So I don't want to find a minimum of the inner product. I want to find the minimum of inf for all F in B and all G in D of the inner product of F and G divided by the norm of F and norm of G and cos inverse of that. So for that I want to compute the infimum, and it has been observed that it is related to the first eigenvalue lambda 0. So this minimum value is greater than equal to cos inverse of root over of lambda 0. So there is a nice proof of this particular statement. So you can basically control the inner product of two signals here and there. Basically you can control the spillover of energy when you are doing time limitation or band limitation and vice versa by choosing the lambdas appropriately, and the values of lambdas are dependent on basically the choice of omega and t, how much band and how much time you are providing. So those things you can do. What more I want to do today? Yeah, I want to talk about a little bit about the application. So in the next class, basically I will talk about the first application, which is the dimensionality theorem. So why I started with this topic particularly, and this particular topic is not there in any of the textbooks. It is not normally followed in any digital communication course because of its a little tricky mathematics. However, I want to start this because this particular analysis of time limitation and band limitation is central in digital communication, which makes this makes it special from and different from analog communication. And also these dimensionality theorems leads us to the Kolmogorov's epsilon entropy that gives us the motivation behind digitization, behind quantization. So I want to do that first, and then I want to move to random process, and random process I want to expand noise, expand random process. Over there we will come into something called additive white Gaussian noise and band limited additive white Gaussian noise. Over there we have to do some eigen analysis again. We have to solve some problem in something called reproducing kernel Hilbert space, the so-called Carr-Hunan-Loew expansion and Mercer's theorem. Over there we will come across the similar kind of integral equation which we have seen here. Let me show you again. Yeah, this kind of equation, because the kernel, the autocorrelation function of band limited additive white Gaussian noise is basically sin C. So this kind of problem will be faced over there again, and we need these tools, the Prolate spheroidal wave functions over there also. So that's why I started with this. So now in the next class I will talk about the dimensionality theorem, and this Prolate spheroidal wave function, these expansions, this will give us a nicer proof of the dimensionality theorem, which is not possible using our intuitive proofs, which I have already stated in one of the answers I have given to some of your questions. So that I will talk about, and after dimensionality theorem, or the Fox theorem which I was talking about. It was called Fox theorem for a long time, then some people tried to call it dimensionality theorem also. We will talk about Kolmogorov's epsilon entropy. And then I'll talk about the expansion of the KL expansion of noise. So these are the immediate application of this Prolate spheroidal analysis, and that's why I did it, of band limited AWGN. So in the next couple of weeks I will be talking about these things. So tomorrow I will talk about dimensionality theorem and Kolmogorov's epsilon entropy, and the fourth lecture I will start probability. I will start probability and random process. Hopefully next week I will be talking about the scale expansion, and by the end of that, when we develop random process in a fairly good way, I will do this Wiener-Fingen theorem as well, and then we'll move towards information theory. We'll construct the concept of entropy, mutual information, etc. And then we will go to quantization, the next step after sampling. So you can see that normally in digital communication course, what is done? Sampling, quantization, boom, we enter digital communication, we enter the digital world. But I am spending some time. Now these things are tricky. Whatever I am teaching, these are a little tricky, but if you can understand, it will give you immense confidence, I can tell you. And moreover, what I am planning, I will give my first assignment, which will be a coding assignment, that will be based on these Prolate spheroidal wave functions. So please understand these concepts carefully, whatever has been taught, and I am providing the supplementary material, the original papers, such that you can go through that. Not everything you can understand, but still get a feel that what they are like, and then like we can design some question about like generating the Prolate spheroidal wave functions, plotting them, and their different kind of like computing the inner product and expanding a signal, a band limited signal using those, and those performing these particular operations B and D in MATLAB. So whatever we can do in offline in MATLAB, we will do. Please give your time. And one thing which is not very encouraging is that you are not not all of you are listening, so that is not good. So in the last class in network theory, that was also a online class, but all the students, they used to complete listening to watching all the videos every week, such that we could move in a better way. But I have given you all the videos, the 8 preparatory videos of Fourier analysis, and now I am not considering like your lack of knowledge in Fourier analysis anymore. You should know everything, and so I am like starting at a higher level in that sense, in terms of the Fourier analysis concept. So please listen to them, ask questions. I'll try to answer over there. If I don't if I cannot convince yourself over there, I'll answer those questions in the next video, or I can make a separate video on those clarifications. Okay, so with that I am stopping today. Tomorrow I will be developing the dimensionality theorem from those Prolate spheroidal wave functions. Okay, bye.